Give her a hand, everybody.
Thank you very much. Can the people in the back hear me all right? Okay, great. So I'm really excited to be here. This is my first time in Norway, and also first time at a security conference. And I'm going to be talking to you about what's going to happen to all of us when our AI overlords take over, or as Dave referred in his previous talk, the AI nonsense. So a little bit about me. So I work on the data team at a company called Elastic. The data team is part of the bigger machine learning group. We do a lot of data analysis, and that's sort of my day job. And at night, I wear a giant bat costume and I fight crime, but in my dreams, not really. By nighttime, I do some reverse engineering on the side, and sometimes I look up some interesting things. So as always, all the opinions are presented here are my own, and the mistakes are definitely my own. So if you see anything, then just please shout out. Right. So I'm going to take you back to a nice warm day in June in 2012 when humanity solved one of the most important problems we've ever had: how to identify cat faces in YouTube videos. This was an article, well, this was a piece of research published by Google where they trained a machine learning algorithm called a neural network to identify cat faces, and I think the data set that they used was YouTube videos. So after this monumental discovery, where humanity was forever changed, a lot of people became very worried because all of a sudden computers were starting to get good at the things that we were good at, so watching cat videos. And so people, I typed this into Google, and this is what people are worried about is going to happen. What is our world going to look like when automation is going to replace all of us? So this was some people's worry, whereas, others were very happy and are going to welcome our AI overlords, for example, into our ovens. So it was quite a surprise to me that a lot of people are very excited about putting an AI algorithm into their oven to adjust an optimal cooking temperature for muffins. Personally, I would be a bit scared to put software into my oven because, those things get very hot. And I'm just dreading the bug where someone forgets to set a safe limit for the oven. But anyway, there's this oven called June, and it's actually already in the second edition, and it's sold out. So apparently it's very popular. You can also use artificial intelligence to brew beer. I haven't tried it, but maybe it's good. And some people even say that in the future, when AI algorithms are doing all the work for us, our society will be transformed and the nature work will be transformed. And as Aaron Bastani published this book, we'll be living in a fully automated luxury communism, which inspired the title of my talk. So I was wondering, in this future where our AI overlords have taken over, what will happen to malware analysts? Will they just be pushing buttons while the AI algorithms perform all the important work? So as you know, a lot of this is hype. And I sort of want to take a step back and just look at a little bit of the landscape from 10,000 feet to understand what's beneath the buzzwords. Throughout history, since we've started trying to develop an artificial intelligence, there have been several different techniques that people have used. And the one that's gaining popularity at the moment, and probably for the past 30 years, is a set of techniques known as machine learning, where we use various statistical algorithms to try and produce computer programs that learn from data without being explicitly programmed. And actually, a prime example of this is something that all of us benefit from every day, and probably one of the first examples of successful application of machine learning to cybersecurity, which is spam filtering. If you think about this problem, this is a computer program that would be very hard to write using traditional approaches. You couldn't just create a rule-based algorithm that would try to match all the possible words that could occur in spam, because if previously you were just filtering out all the emails with the word enlarge something, spam writers would try to out-trick you by, substituting numbers for letters, and then your program would break and you would have to retrain it. But with machine learning, your algorithm will automatically adapt to changes, and it will start to associate that new word with a higher probability of being spam. And therefore, it will automatically sort of retrain itself. So this was definitely one of the first successful use cases of machine learning for security. Now, if you look at the general landscape of machine learning, we can roughly break it up into 3 different types of sort of movements. There is supervised machine learning, where you are training your algorithm to classify data points into known classes or to give you some sort of values. So for supervised use cases, you will need to provide a labeled data set. For example, you have a labeled data set of binaries that are malicious or normal, and you could use this to train a supervised algorithm. The second big strand of machine learning algorithms are called unsupervised. So here you're not using any kinds of labels, but instead you want the algorithm to tell you something interesting about the data. Clustering is a prime example here, where you simply give your algorithm a big chunk of data, and you tell it to group those data points into interesting clusters that might be useful for you. So a prime example here would be, let's say, using an unsupervised learning algorithm to group your malware samples into different families. The third area is something called reinforcement learning, and I haven't seen much of that in cybersecurity applications. Here you basically have an intelligent agent that tries to make decisions about data points and then gets feedback from its environment so it can learn more. But as I mentioned, for cybersecurity, the 2 main things that I'm going to focus on is the supervised use cases. So here, your algorithm is trying to take data points that are labeled with known classes and then learn some kind of distributions about them, so that when you have new unseen data points, the algorithm can see, oh, this data point is closer to that cluster, so it must belong to that class. And likewise, in unsupervised learning, you would have just a big blob of data, and then the algorithm tries to figure out how many clusters you have. And this is a sample from a very popular open source machine learning library called scikit-learn. And you can see in this picture, they've applied different kinds of clustering algorithms to this data set, and then it has produced those different kinds of clusters. So in both of these classes, the supervised and unsupervised learning algorithms, there are many different versions you could choose. And there is a concept that we have in machine learning called no free lunch, which means there is no single algorithm that will perform better on all data problems than all other algorithms. So you can't just walk up and say, okay, now I will always be using support vector machines because they are the best. That's not the case. Instead, you have to do a lot of experimentation. And this is where part of the so-called dark art of machine learning and data science comes in, is that you have to do a lot of experimentation and a lot of trial and error to really get this right. Now, this is also where someone like me, who mostly works with data, can learn from someone like you, who work in the information security field. Because algorithms are context agnostic. They don't really care if the data point they're trying to classify is coming from a malware sample, or if it's coming from an intrusion detection system, or if it's coming from, let's say, some customer data from marketing department. All they care about is the numbers that are coming in. So it's really up to the malware analyst and the data scientists to collaborate together to come up with a good way to represent, let's say, malware samples, so that we actually work on problems that are meaningful. This brings us to our next big problem when we're trying to apply machine learning to cybersecurity. How do you actually, if you want to do classification on binaries, let's say you have a set of binaries that are coming in through your honeypots and you want to determine which are malicious and which are not. How do you actually take that binary and transform it into a data point? what kinds of things about it do you compute? Do you take the virtual size? Do you take the number of strings? What do you do? This is what we call feature engineering. So you want to compute statistics about your binaries that would give you a good separation between malicious and benign classes. So suppose you would say, OK, I'm going to use the size of the binaries to train my data. If the distribution of sizes is the same in the malicious and benign classes, you won't get very far. So what have people used in the past when they wanted to classify binaries into malicious and benign? I've looked at a lot of literature surveys going back to 1995, and some things that people have used are, for example, function names, the names of libraries that binaries import, Byte histograms, sequences of function calls, and strings present in binaries. Now, most of these are great, except that, for example, for strings and function names, they are very easily derailed by the fact that people usually use packers or obfuscators. So this is also something that we have to take into account. Now, after you've selected your features and you've trained your algorithm, you, of course, have to find a way to evaluate your results. And if you're ever working in an organization and you're trying to evaluate a machine learning solution, this is something that you definitely have to take into account. How has the vendor evaluated that their product is really working? So this is not actually as easy as it looks. You could say, OK, I'm going to take my features, my algorithm, and I'm going to train it, and then I'm going to see how many times it gets the classification right. But let's say you had a data set with 99 good binaries and 1 malicious one. Your algorithm could simply be saying benign all the time, and it would be right 99 times out of 100. So accuracy alone doesn't actually tell us much about how well we've trained our algorithm or how well it's performing on new unseen data samples. So what we actually do in the machine learning space is a bit more complicated. Algorithms don't usually output simple labels like benign or malicious. Instead, they output a probability that a given binary is malicious, or they output some sort of score. So we take these scores and we compute what's called a receiver operating characteristics graph that looks like that, which tells us the true positive rate and the false positive rate at different thresholds. And then we compute the area under this curve, and we try to get it as close to 1 as possible. So if you're ever going through literature on machine learning, you might see these kinds of metrics being used to evaluate classifiers. When you actually try to put this into production, as I've learned in my daily job, things get complicated very quickly. Something that works well on your laptop does not work well when it's scaled to terabytes of data. You have to train the data, you have to clean it, you have to gather it, you have to evaluate it. And the way the sausage is made is usually not very pretty. This is also something that you should keep in mind if you're buying a vendor solution that uses machine learning. How well are you going to be able to interpret the results that it gives you? Usually in this space, when we want to push performance, we sacrifice interpretability. The state-of-the-art algorithms that give us the best results are usually the ones that are hardest to understand. And in many industries, for example, banking and insurance, it's very important for compliance purposes to be able to understand how the black box is thinking. And I think the same probably applies to cybersecurity as well. If an algorithm classifies something as malicious, you want to be able to at least have a good idea or an understanding of why it did this. So definitely something to keep in mind. So beneath all this hype, I think it's worth for us to ask, is this AI nonsense that we're trying to introduce into our systems really worth it? Because ultimately what you're doing is you're unleashing a massive hulk of complexity into your system, and you don't even know if it's going to be worth it in the end. So I tried to go through the literature and see some reasons why people might want to introduce ML into malware detection. And one of the reasons that kept coming up in paper after paper is that in the past 30 or 20 years, we've seen an explosion in new ways to generate malware samples. So what 20 or 30 years ago might have taken an expert to write a virus, or someone really dedicated, is now actually pretty easy. I mean, you have script kiddies selling Mirai botnet variant on Instagram. So because of all this leaked source, and actually even open source malware, we've seen an explosion of new malware samples. There was an estimate by Symantec that in 2010 alone, there were 286 million unique malware variants. So as you might imagine, if we're using the traditional approach by antivirus engines where we have to examine the malware and use heuristics to develop signatures for detection, this is going to get really hard really quickly. And we're going to have to start hiring more malware analysts if we're going to cope with this kind of explosion in malware. So essentially, one good argument to try and automate this is that we simply have too much to do with the people that are currently working in this industry. So I decided to take a look and see how practical would it actually be to automate malware detection with machine learning. And I looked at the literature. I looked at the literature going back to 1995. Now, we all know that the industry and academia are often very far apart, and industry has definitely had a very optimistic outlook on introducing AI nonsense into our stacks. If you look at venture capital funding that's flowing into cybersecurity, you see that a lot of this funding, and very large amounts, is going to different kinds of AI solutions. Not just solutions that automate malware analysis, but all kinds of things. User behavior monitoring, anomaly detection, you name it. Autonomous threat hunting machine. It actually sounds a bit scary, like Skynet or something. But anyway, yeah, there are some people that are saying that this hype is actually a bit dangerous, because if you think about it, you're really introducing something into your security stack that you don't fully understand. And I sort of agree with this a little bit, is that you should exercise caution. But anyway, let's move on to academia. So what do the academics think? And what kinds of breakthroughs have we seen in academia in this space? So actually, this is not a new thing by any means. The problem of automatically detecting malware has its roots in at least 1996. This was the earliest reference that I could find to any kind of research that was using machine learning techniques to detect malware. So this was a group at IBM. They were trying to develop a new kind of antivirus engine that could classify boot sector viruses. Apparently that was a big thing. I actually don't remember this far back, so maybe some people in the audience will know. But yeah, this was the first paper where people were using these techniques, and they actually were not very successful because the way their implementation was done, they could only work on very small viruses. So then fast forward 5 years, and we have a paper by a research group led by Dr. Schultz that was really the first paper to take PE files, so executables that can run on Windows, take the strings out of them, convert them to data points, and try different kinds of classifiers like Ripper and naive Bayes. The sample sizes used in this study were very small, in the thousands, so they weren't sure if this could really scale higher. Although they did get some promising results, in later papers, people have sort of questioned how well this could work in practice. So 5 years forward from that, we have a really cool paper that uses lots of techniques that we use for spam classification and text classification for malware. And I was actually quite excited to see this paper because it was the first paper that I found where people weren't using strings or function names that they extracted from binaries, but actually the byte sequences that were found in binaries to create these feature vectors. So what the researchers in this paper did is they used hexdump to convert the binary code into what they call n-grams, so little bits and pieces, and then they put those together into giant feature vectors that were then used to train these classifiers. And they actually had a bit of success doing this. So with the, I think, 4,000 or 3,000 samples that they used, they were able to get accuracies, which is not a great metric, but still, they were able to get accuracies of 92 to 95%. So that's actually quite good. Let's move 1 year forward. And we have this really interesting paper that didn't really get much attention, but this paper made a hypothesis that you can actually use the opcodes in disassembled malware to predict which binaries are good and which binaries are bad. And I thought this was very interesting because I had never thought about it this way. So this researcher, Daniel Byle, he took a set of known good binaries from his Windows machine, and then he took a set of viruses, and he disassembled all of them, and he looked at the bytecode distributions for benign and for malicious ones. And he found that there were some slight differences. And moreover, what he found is that you can actually, the presence of really rare bytecodes can actually be a good indicator if something is malicious or not. And this was actually quite cool because as a data scientist, I often find that features that we use in machine learning don't have much correlation to the samples. But here you can see that, for example, NOP, which has a high correlation of being associated with a malicious virus, is actually something that has a functional meaning for the virus. Many virus makers use NOPs to pad their binaries, and I thought this was quite cool. Right. So this research has been used in other papers as well, and I think there are some attempts to use more opcode classifiers to predict malware. So fast forward to what people are doing now is the trend in research for this kind of stuff is using more visual methods to classify malware. And this paper was really cool because the researchers computed different kinds of statistics from binaries, and then they used them to create RGB images. So actually, your malware were converted to different kinds of visual representations, and then you can see from the images that different malware families produce different kinds of images, and then this was fed into classifiers that could further classify this. So what I've learned through looking at a sample of these papers is that there are lots of challenges in applying this technology, even in an academic setting. So as I look back at my research, I wonder if the vendors who are claiming that this works in production today have really done their homework. In the papers that I looked at, most of the samples were really small, in the sizes of maybe maximum up to 1,000 binaries. So I really wonder if this can scale to production. And if you're ever evaluating a solution that claims that it can do this, I would definitely ask some serious questions. For example, how has the vendor made certain that their training data is representative of the malware samples that are out there? So moreover, what we really have in this field is lots of challenges in making this scalable and making this to production. And one of those challenges is that we don't really have a big public data set of benign binaries. In the papers that I looked at, most of the data sets were proprietary. And even though you can probably get lots of malicious binaries from places like Virus Exchange or Virus Heaven, we don't really have good places to get benign binaries because most of them are copyrighted. So you can't really share them in public, which is usually what's very important if you're trying to do data science development, is being able to share data sets. The second challenge that we have is labeling a data set. If you remember what I was talking about in my slides on supervised learning, most of these classifiers require some kind of labeled data set to train them. So we don't really have a large-scale automated way to analyze malware to train it. It usually requires someone who is an expert to take a look at it. Or you might want to use an external service like VirusTotal, but it's known that it's flaky and those classifications do change. So that is definitely the second challenge. And the third one is you don't want someone like me running around with 10,000 samples of a virus on a USB stick and sharing that with my colleagues. That might definitely not end well, because unlike you, I'm not a professional in handling this kind of hazardous material. So there were a bunch of researchers at a company called Endgame that saw these challenges, and they decided to do something about it. So they developed a data set called EMBER, the Endgame Malware Benchmark for Research. And this included 1.1 million portable executable files, some of which were benign and some of which were malicious, collected in the years 2006 to 2017. And they computed some statistics, some features from each of these binaries, and they released it out into the public. And as I was doing research for this talk, I decided that it would be interesting to take a look at this data set. So unlike the data sets used in the previous papers, this didn't actually include the binaries themselves, because most of the benign binaries are copyrighted by Microsoft, so you can't distribute them. But they all include the checksum. So if you're doing research, you can take this checksum and go back to VirusTotal and look at and track down the sample to see what it is. So what kinds of features did the EMBER researchers compute? So first, they had just some general statistics about every binary, such as its size, how many imports it has, and so forth. They also extracted a lot of information about the strings. Because if you remember back to my section on academic research, strings are one of the important features that people often try when they try to develop classifiers. And something that I found very interesting personally is that they computed byte histograms. So they took every byte from 0 to 255, and they counted how many times the byte occurs in the binary, and then they published this histogram. So I started wondering if it would be possible to develop something called a byte histogram fingerprint to see if the byte histograms between malicious Windows files and benign Windows files were different. And the reason that I started doing this is that I had seen this tool published by CERT. It's an Austrian website, I believe. And this tool uses this technique of byte histograms to detect if a malware has been packed by a packer or not. So on the left-hand side, right-hand side, you can see that an unpacked malware has a byte histogram that's not very even. Whereas if it's packed, you can see that it's completely even. And this is sort of a great statistical way for you to detect if something has been packed. So I decided to see if we can get anything interesting by computing a large-scale view of all the byte histograms in this data set. So because there were 1.1 million binaries, I wasn't able to process all of them, but I took a sample of about, I think, 130,000 malicious Windows binaries and 160,000 benign binaries, and I created a picture of all of the byte histograms. So on the horizontal axis, you have the number of the binary sample. So each one of these vertical lines represents one binary. And there on the vertical axis, you have the bytes. And the lighter the shade on the picture, the more of that byte is present in the binary. And the darker the shade, the less. So I was very excited when I first generated these images, because you can clearly see that there is a difference in the byte histograms between the benign files and the malicious files. So I started to take a closer look at some of the interesting features I saw. For example, what is that? It's like a binary that has zeros on most bytes except a few. And likewise, if you look at the benign picture, you can see that there is something that looks like a track going right across the image. That's an increase in counts of bytes between 100 to 125. So I thought that was interesting too, especially because you don't really see it in the malicious binaries. So I zoomed into this picture and I extracted the sample that's represented by the dark line, and I decided to see what it was. So this turned out to be a variant of Cosmic Duke, which is like a spyware Trojan, I wasn't able to find out why the byte distribution was so skewed that most of the bytes are actually zeros. I suspected that maybe there was some kind of pre-processing going or some sort of packing. But what I wanted to see, if all of the dark lines in this picture above were the same kinds of samples. So I looked at another one, and this was also Cosmic Duke. So this is actually quite interesting, because I wonder now if this kind of visualization technique could be used to maybe automate some of the detection of this kind of malware. Another thing that I noticed when I zoomed into the picture is that it looked like some of the lines were completely gray. So there was no variation in the byte count. And I started to wonder why this was. So if you remember a few slides back, I showed you that when a sample is packed, the byte distributions become very even. So I wondered if this was the case here as well. If you see a completely gray line, it means that the sample is packed. And I was actually excited to find out that I was right. So this line that I picked out represents a Zuzi. I don't know, it's a very creative name for a Trojan. But it turned out to be packed. So this was also quite exciting, because it shows you that this kind of visualization technique can give you a quick overview of a large number of samples, and can tell you something meaningful about them. Right. So another thing that I mentioned before was this interesting swim lane in the middle of the benign malware binaries that's kind of present in the malicious ones, but it's not as clear. And I wondered why it was that we saw this in the good malwares, good binaries, but not in the bad ones. And when I asked my friends on Twitter, they hypothesized that this was because this byte range represents the printable ASCII characters, and those are often stripped out in malicious files to help avoid detection. And I think that could actually be true. So this is something that I'm going to investigate further. So in summary, what we've seen so far in this whole talk about AI nonsense is that doing this kind of stuff is very hard. The academics haven't been able to get it right, and I'm not sure the industry is at a point where this can be reliably deployed to detection, reliably deployed to production. But, however, the number of new malware binaries is increasing quite rapidly, so we definitely can't probably rely on malware analysts alone to help us detect new samples. So some sort of machine learning methods will probably definitely be introduced in the future. We've also taken a look at the process of developing a machine learning classifier. So we have to be careful about our feature selection. We have to select our algorithms, do experimentations, test and evaluate our classifiers. The progress in the field is currently being hindered by the fact that we still don't have great public data sets apart from EMBER, and we don't have any benchmark algorithms. So when you're talking to vendors about introducing a malware solution, you don't really have any kind of benchmark that you can use to evaluate what they're proposing. But luckily, we have this EMBER data set that can help us fix the gap. So lastly, I just wanted to say that it always takes a community to bring someone to a conference. And in my case, I want to say thank you to a community started by Marianne Marshallak, Black Hoodie, which I attended last year. If you don't know about it, Black Hoodie is a group that aims to bring more women into reverse engineering. So this is definitely one of the reasons that I am doing this work and why I'm here. So definitely a big thank you to them. And also thank you to all of you, and I'm happy to take any questions that you have.
Hello, does anybody have any questions? Malware, machine learning? Yes, thank you.
Hey, I just want to say thank you for a great talk. I have a question. Once these vendors may be able to actually detect malware, And I'm guessing that the malware authors also will adapt their tactics in order to try to subvert AI. How do you see that kind of play out in the future?
So this is that's a great question, because there is a lot of talk going on about this AI versus AI in cybersecurity, and I think I would reiterate what Dave said. We're not at that point yet where malware authors would even need to use that, because there is a lot of low-hanging fruit in breaching organizations. So you don't need to go to the trouble of developing malware that can evade a machine learning classifier. However, that being said, last year at the Black Hoodie conference, I saw a great talk where someone had trained malware communication to a command and control server to look like the communication of Facebook Messenger, so it could evade detection. So, I mean, in terms of academic research, it is possible to do that. So if you're a malware author, you could certainly do that, but that's a lot of extra effort, and I don't think we're at the stage where they need to do that yet.
I thought I saw you as working for Elastic.
That's correct.
Do you know of any current or coming projects or tools using Elastic to analyze or kind of productionize the data coming from such malware analysis into Elastic, for example?
So I guess, I mean, our tools are more generic data analysis tools and data visualization tools. And I don't know of any current project that would develop something like this. But I mean, it certainly is possible to put this data into Elastic, because I've done it. So if you want to talk to me offline about it, then I'm happy to help. But I don't think we have any specific products that are coming up for malware analysis.
Anybody else? All right. Someone at the back.
You said when you looked at some of the black samples from your histograms, you weren't able to determine why they looked like that.
No, yeah, you're correct. So I looked at some of the samples that were completely black, and what I saw in them, that most of the bytes were concentrated from 0 to 5, and then the rest of the bytes were close to 0. So for some reason, this binary had a lot of those bytes, but none of the others. And yeah, I wasn't able to determine why this was. So I'm hoping I can find a way to get the actual file from VirusTotal so I can, you know, disassemble it and take a look at it.
That was kind of my follow-up suggestion, that convince someone with VirusTotal intelligence or something that can get you the sample to actually give you the sample you want.
Yeah, I think that's a great suggestion. I think there is a premium subscription or something that you can use to pull samples from VirusTotal.
All right. Thank you very much, everybody. And thank you to our speaker, Camilla. Let's give her a hand. And we have a small token of our appreciation. There you go.
Thank you very much.
Thank you.
Is this alcohol? Sorry, the reason I'm asking is that I'm originally from Finland, and we smile even less than the Norwegians until we get alcohol.
I'm not sure you're allowed to open that in the venue, but
Okay.
please enjoy it later.
Thank you very much.